Hello everyone, thank you to the organizers for the opportunity to present my work that is in collaboration with Jorge Cervantes at UNAM in Mexico. Today I will talk about testing the Symmetron with full shape technique. Um, we know that lambda CDM is a very successful model to explain some cosmological observations like the BAO and CMB. However, there are some issues like the coincidence problem and the very observed value of dark energy when E is compared with the value obtained from particle physics, for example. And also, recent observations like DESI and DES suggest that lambda CDM is not the best fit to the current data. So this is a motivation to consider some alternative models. Indeed, DESI and DES suggest that dark energy could be a dynamical dark energy instead of a cosmological constant. So DESI and DES show that for WCDM and W naught WACDM are a better agreement with observations. But also we can consider some modified gravity models to explain the cosmic acceleration without the necessity of cosmological constant. And upcoming surveys like DESI, SSST, and Euclid could allow us to test this gravity at cosmological scale, for example, considering power spectrum or the correlation function in cases, even using, for example, the Weyl spectrum or other observables. Okay, here let me say the pipeline, the full shape theory. In particular, we are considering these two modified gravity, Symmetron and Husaviki FFR model. And this pipeline is based on the FOLPS-nu code that is already used in DESI. But in my case, I implemented this to modify gravity. And then first, we have the input cosmology that consists of the cosmological parameter, like the baryonic density, the matter density, the spectral index, etc. And these parameters enter into class to compute the linear power spectrum. Then FOLPS-nu compute the linear power spectrum for modified gravity model, and use this linear power spectrum for modified gravity to compute the nonlinear power spectrum throughout the RSD, the bias scheme, considering the EFT counterterms and shot noise terms. And this is used to compute the infrared resumation for the multiples. And this full theory is used in the MCMC analysis for doing the parameter estimation. Here, there are two key aspects to comment on the Symmetron model. For example, the Symmetron and the FFR model. That is, then when we can take a modified gravity model, we have a scale dependent in the growth rate and also in the kernels. So, for example, for the scale dependent growth rate, the implications are in the computations even at linear scales, not only and nonlinear and quasi-linear. And when we take or when we consider the full kernels for each modified gravity models, this scale dependence is complicated because the computational cost is very high. So in this sense, we can use the fk-Perturbation theory approach that consists on take the limit on large scale on the kernels. That means that we take k equals 0. So these kernels are reduced to the lambda CDM case, and this is the better for the computations for the MCMC analysis. Okay, here are show the basic theory or relevant theory for the first model, Husaviki. We have the Poisson equation, that is equation 1, but with the help of the equation 2 related to the scalar field and the potentials, we can compute or derive the modified equation of Poisson that has this form. And we can see this mu function that is important, that is the relevant, at least at linear level, because in this function is the k depends. So we can see some important things. When k equals 0, these terms vanished, and so we have the GR case, mu equal 1. But when k is with this condition, that this condition depends on this m1 function, that in general is scale and time dependent, we have that the Newton constant is boosted by this factor, and this function is relevant for the linear calculation. Okay. Then for the Symmetron model, we know that there is a general action for a scalar field, a key, and here we are showing some relevant functions. The scalar field for Symmetron model has this form, but this Symmetron model present a behavior that is curious because we can define a transition value at which the symmetron begins to act. For example, in this particular work, we are fixed this value at scale factor equals 0.5. So uh, for values at the beginning of the universe, at the early universe, the model is fixed to lambda CDM, and at this transition value is when symmetron begins to act. And then we have the coupling parameter between matter and the scalar field, with m is a scale mass that has these constrictions, and we have the potential. This potential depends on some constant mu and lambda. Mu has a mass units, and lambda is a dimensionless parameter. But also we have to consider the effective potential, not only the original potential, because uh, like it is showed in the original work of Symmetron, this potential is not sufficient to explain the cosmic acceleration, so it is necessary to consider this contribution of dark energy. And then we have the mu function for the symmetron model that we can see is similar for f of r case. However, appears these two functions, the coupling function and the beta function. Beta function is related with this transition value because this functionality is it's already appear into the beta function. Here for beta, we have a beta 0 that is a parameter, important parameter for this modified gravity model. And we consider the two cases, like in the previous slide. K equals 0 corresponds to GR, and for this constriction for the scale, we have that the Newtonian constant is boosted by this term. Here, A is of the order 2 unity, so is 1 plus 2 times the beta 2 square. Okay. So when we consider this scale dependence, we have to solve the differential equation for the growth rate. And here we can see two key aspects, two relevant aspects on this equation. First, we have this term into the square parenthesis. However, this is of the order that in the lambda CDM case. So it is we can replace it by the lambda CM case. However, here appear the mu function that is the contribution of the scale. So when we take the differential equation and we solve, we can obtain the two cases when the function is in terms of the redshift. Here in this slide are the results for the growth rate in function of the redshift for 2k beams. We can see that for these figures, the symmetron that correspond to the blue curve in the two cases is of the order of the F6 model. And we know that F4 and F5 are rolled out in recent observation by recent observations. So for completeness, we are showing. But the important thing is that symmetron is of the order of F6 in function of the redshift. Okay, for the 2k beams. However, we have done the same computations, but now with the group rate in function of the scale, and we can see three plots. On the left, we are showed the case of redshift equals 0.8, in the middle redshift equals 0.5, and the left in the right zeta equals 0. Okay. Again, Symmetron is the blue line and F6 the orange line for f of r, and the horizontal line is the lambda CDM case. So we can see that for today, at the redshift equals 0, uh, again, Symmetron is of the order of the F6 model. And through the redshift 0.5 and 0.8, we can see some discrepancies or deviation with respect to F6, but this could be important to at the moment to do the calculations for the multiples and even for the MCMC analysis. So here, let me show quickly the full one-loop power spectrum that correspond on this first expression that take into account the linear power spectrum and the pure one-loop contributions. The linear power spectrums is taken for these three expressions that, if you can see, is the linear power spectrum, but boosted by the curve rate dependence. Okay, the dependence of the curve rate. And then we have the pure one loop contributions, and we can see the f, g functions that correspond to the kernels that in general for modified gravity are scale dependent. Okay, and here this is the complete theory, that is the power spectrum, but considering the moment expansion, the EFT power spectrum, and the shot noise power spectrum, where the moment expansion is given by this expression. Again, appear the function here in the power spectrum, pure one loop power spectrum contributions, appear the curve rate in terms of the scale, but also the TNS model and this D function. For the EFT contribution, we have these constants, but also the contribution of the Kaiser power spectrum and the shot noise. And we use this infrared resolution scheme that basically is separate the power spectrum into parts, one when considering the wiggle part, and another not considering the wiggle part, so the non-wiggle part. And it is the function, or it is the expression to compute the multiples in here, and then for doing the MCMC analysis. Another important thing to say about the Symmetron is that the FK kernel approximation is tested or is validated fiercely in our work. Here we are showing the results. The solid lines correspond the monopole in orange and the quadrupole in blue, taking the full kernels of the model. However, when we use the FK kernel approximation, but also considering these corrections of the EFT types, um, like EFT of this form, we can see that the deviation with respect to the full kernels are around 1%. This gray line corresponds to the 1%, so we can see that the deviation are of the 1% at k equal to 0.2 approximately. Okay, so we can conclude that the FK kernels approximation is in agreement with, or is good for approximate or for computations in Symmetron model. Okay, and here only show the FK kernel approximation. That is take the large scale limit, consider k equal to 0, so those kernels reduce to the lambda CDM case at large scales. And here we are shown the main results for our work, that is in preparation. Here is the validation of the pipeline and the code, the FOLPS-nu modified code for f of r model, and consider the EBOS data release 16, and only the North Galactic Cup at this effective redshift. And we can see that for the f of r parameter, This is the construction that is in accordingly with the values that we are expecting for data. And we can see that the cosmological parameters are recovered, are estimated that in a good agreement with GR, for example. And yes, okay. And the other parameters are not shown here, but we are using flat priors in all the parameters except for baryons. That is a Gaussian prior. Okay, centered in the BBN prior. Okay, so this is the result for f of r. So we can do the same for the Symmetron model, and this is our results at the same effective redshift, considering the same data. And we can see that beta 0 is constrained at this level. And again, the cosmological parameters are in agreement with GR or lambda CDM, no? Even the linear bias. Okay, some important to say is that here we are using we are considering the k range between 0.01 up to 0.18. Okay, so the max k value is 0.18 and taking this data. Okay, so this is our results, considering the free beta 0, but also in future works we can take another symmetry parameters to be free. For example, the case of the mass function, we can keep a M0 parameter free, and we can see what is the parameter constraint for two of the parameters, okay, for the Symmetron case. And we can see if we obtain a better results or another distinct results, okay. Yeah, but okay, this is all. So thank you very much, and I hope you are enjoying the dark energy from home. Thank you very much.